In the second example, we need to identify the quadrilateral as specifically as possible. We need to clearly show and explain all of our work to get credit for this, to be a coordinate proof. These are going to be the most common types of coordinate proofs that you'll see. They're kind of long and difficult and annoying, but they are nice challenging problems that aren't actually all that challenging to do. It just involves lots of pieces. So let's start out by looking at some side lengths. So any kind of quadrilateral like this, you're looking at slopes and side lengths to prove things about it. You could also look at the diagonals if you chose. So let's look at our first side length, A to B. Our change in the x's is 2. 1 and -1 are 2 apart. So we have 2 in the x's. We'll square that. Plus difference between 3 and 9 is 6. So they're 6 apart. So our y's are 6 apart. And let's square root that. So 2 squared is 4. 6 squared is 36. That's going to be square root of 40 when you add 36 and 4 together. So our distance here is square root of 40. And let's see what we get going in this direction here. 1 and 3 are 2 apart, and 9 and 3 are 6 apart. So we're going to have the exact same thing. We're going to have a square root of 40 again. So another side that's the same. So these two sides are the same. Over here, 1 and 3 are 2 apart, -3 and 3 are 6 apart. So we are getting used to that pattern. That's also going to be square root of 40. And then 1 and -1, 3 and -3. That's going to be 2 squared plus 6 squared for a final time, giving us another side length of 40. So all 4 sides are the same. So right now we already know that we have a rhombus because a rhombus has all 4 sides being the same. The only thing left to check for the most specific name here is whether or not we have a square. Now, if you're looking at this picture and you've made it past the first grade, you're probably thinking, I don't think that's a square. It doesn't look like a square. I agree with you. I don't think it looks like a square, but let's prove it. And one way we can prove that is by proving that this is not a right angle, that these lines here are not perpendicular to one another. So let's find some slopes to do that. Slope here is always the rise over the run, the change in the y over the change in the x. So change in y we said was 6. So 9 minus 3 is 6. So now we're talking about slope here. 6 on top. And then 1 minus 3 is -2. So our x is on the bottom. 9 minus 3 is 6. 1 minus 3 is -2. Get a -3 slope. Common sense check, it's a slope that's going downwards, so yes, it should be negative. It looks pretty steep, so -3 makes sense. On the other side over here, we go 3 minus -3, that's a change of 6, over 3 minus 1 is a change of 2. We have a slope of +3 over here. Now, these are the positive and negative of each other, but they are not the reciprocal. A slope that would be perpendicular to 3 would be, or to -3 would be +1/3. But we don't have +1/3, so let's get rid of that. They are not perpendicular. Not upside down T, not perpendicular. So we've proven that we have a rhombus. We've checked to see that it cannot be more specific, that it cannot be a square. So we have a rhombus, and we've proven it. Next one says a quadrilateral has 3 of the following vertices. Find the 4th one that will make it, first of all, a rhombus. A rhombus has equal side lengths. So this right here, this length here, if we go 1, 2, 3 over, and then 1, 2, 3, 4 up, and we do our distance here, 3 squared plus 4 squared, square rooted, is going to be square root of 9 plus 16. Square root of 25 comes out to a nice clean 5. How about that? By the way, get used to 3, 4, 5 triangles. They will pop up all over geometry. So whenever you see a right triangle with a side length of 3 and a side length of 4, your hypotenuse is going to be 5. We know that this length right here is also 5 because we can count boxes 1, 2, 3, 4, 5. Now for the first one, A, it says find the coordinate that will make it a rhombus. If we want it to be a rhombus, all 4 sides have to be length 5. So let's go from here and let's count over 1, 2, 3, 4, 5. And then let's check to see if our fourth side would also be a length 5. We have a distance of 3 and a distance of 4, and we know that 3 squared plus 4 squared square rooted, as we proved over to the left, is going to be equal to 5. So all 4 of those sides would be 5, which is what we want. So the coordinates here would be 5 over 0 up. 5, 0. Next one says Isosceles Trapezoid. So let's clear that out. To be an isosceles trapezoid, we need one pair of parallel sides and then 2 sides the same length that are not parallel. So let's go ahead and draw our other side going the other direction. 1, 2, 3, 2, 3, 4 down. So if we did this, we would still have our side length of 5, making this side and this side the same length, congruent. These two, since they're both 0 slope, would be parallel. So our coordinate would be here at 11 over 0 up. And then finally, a kite. Remember, the rule about being a kite is that you need to have 2 sides that are the same length, 2 consecutive sides that are the same length. Taking a little bit of the slacker approach, we know that rhombuses happen to be kites because the 2 adjacent sides are congruent, these 2 sides are congruent. It just happens to be a coincidence that all 4 sides are congruent. So all rhombuses are also kites. So if we want to be lazy here, let's take advantage of the rhombus and say that the kite can serve, or the rhombus can serve as a kite as well.